Okay, so in this video we are going to analyze a block type brake. So look at here, this problem 16.5 from Shigley's book. So we have block type hand brake shown here in this figure, has a face width of 1.25 inches. So let me write this down here. Face width 1.25 inches, and then the width or depth, mean coefficient of friction of 0.25. So let's see. Then for an estimated actuating force of 90 pounds, so this force F is 90 pounds. F equals 90 pounds. Says find the maximum pressure on the shoe and find the braking torque on on that cylinder or the or rim, whatever you call it, or the wheel. Alright, so this type of brake, its mechanics is similar to this guy. So what you studied in the book, external contracting brake. So how it works, you see this, we have a pivot here, right? So I want to show you the resemblance here. We have a pivot, this pivot is here, and then what else we got? We have the mechanism, rotating mechanism about the the pivot. So actuating force F here, right, is pressing the shoe on the cylinder and causing braking torque. So look at here, we need to so the formulas here I have under this section, 16.2, 16.13, it's like a moment caused on the arm by friction, moment caused on the arm by the normal force, and then relationship between actuating force and those guys, Mn and Mf. If it is a self-energizing system, non-self-energizing will be this, self-energizing will be this relationship, and if you're interested in Rx and Ry, we can find those. The problem was not asking for those, but it was asking for braking torque on the disc or the cylinder. For that one, that part is similar to this equation. I will talk more about this when I calculate this, but the torque applied to the disc, braking torque, will be FRDN. And then, so if you see here, this one, the derivation I did here was was internal, but if you simplify this equation, it's gonna result simplify to this 16.6. This equation is still applicable to that problem I showed you, because that integral is the same. But you need to figure out theta 1, theta 2, B, A, and everything you see in those equations. So let me come down here and see what we got. Okay, so A is the distance from the center of the disc or cylinder to the pivot. So let's see where we have it. So A is this distance. See if my tablet stopped working. Alright. It's not gonna see. Move this. Let's see what's going on. So we need to find the distance between center of the disc or the cylinder from the pivot point. So this distance from here to here is called A. So if I connect this, try to have a straight line. So that distance is A. So how do I find it? If I build a right triangle here, this is 6 inches, this distance is 8 inches. Okay, so A equals radical 6 squared plus 8 squared. We need to find this guy. Let me write this down. So 6 squared plus 8 squared, and then yeah, so it'll be 10 inches. Yeah, alright. Yeah, let's see if we did it right. 64, 8 times x is 64. Let's see, yeah, 64, and then 6 times 6 will be 36, so it will be 100, so that looks right. Alright, so that's the A. Let me show it here. This is my A. So we have that, and then what else we need to figure out? If you look at our equations here, theta 1 is the angle measured from the pivot where the shoe starts, and then theta 2 is where that ends, the shoe ends. So let's look at here. So we are gonna start defining our angle from this line. This is like my x-axis. So one angle I have here is this guy. This angle is theta 1, and then the other angle theta 2 is basically, as you guys see, this is theta 2. So theta 1 and then theta 2 is basically 90 plus whatever that angle is, the theta 1. So how do I find the theta 1? So let me see. Let me erase some of these stuff here. Alright, so theta 1, look, this angle is like 45, no, let me see. Yeah, from here to here, this angle is 45, because this entire thing is 90 and half of it is on the left, half of it on the right, so 45. This theta 1 angle, how do I find it? Let's see. Okay, the remaining angle here, if this one is 45, this remaining angle from here to here, this one is 45 too. So this theta 1 I showed here is actually the difference between 45 and, let me see if I can zoom it. Yeah, so this angle is 45, and this theta 1 is actually difference between 45 and this angle, the other angle I'm going to show here. Let me show the different color. This angle, this guy. If I call this angle alpha, then theta 1 is basically, theta 1 is 45 minus alpha, right? Yeah, theta 1 is 45 minus alpha, and then alpha is 45 minus alpha is arctangent of, okay, let's look at here. This is 6, this height is 6, this is 8. So arctangent of 6/8. Alright, so let's see. Alpha is 6 divided by 8. Arctangent of that guy is 36. So if I subtract this from 45, yeah, so how much you get? Oh, I'm sorry. Okay, let me redo it. 6 divided by 8. Arctangent of this guy. Alright, minus 45. 8.13. So 8.13 degrees is going to be theta 1, but theta 2 is 98.13 degrees. There you go. So we found theta 1, theta 2. What else? Theta 1, theta 2. We have the A. Okay, the radius of the disk, by the way. Let's write that too. The radius, we know it already, it's 6 inches. Alright, so, okay, what else we need to know is the C. C is the distance, it's like a moment distance of F from the pivot. So let's see what that guy is. For that, this is my pivot. Let me erase the stuff I don't need. Okay. Distance between the moment distance between the pivot and the force. So if you go down, right, this is, yeah, it's obvious. C is actually 8 plus 12 is 20 inches. Alright, so we have everything set up right now. I mean, we have all dimensions we needed. So let's look at our equations. Alright, so let me see what this guy is doing. Alright, so MF, moment caused by the friction force on the R. This is the equation. Let me see if I can remember this and rewrite it here. Let's make this a bit smaller. Alright, so MF equals integration of, yeah, okay, FPA, let's see, FPA, what else, BR angle goes from theta 1 8.13 to 98.13, but remember these guys must be in radian. And what, sine of theta, and let me see, sine of theta, r minus a cosine of theta. Yeah, d theta. Alright, so let's see. By the way, since this the shoe extends larger than 90 degrees, so theta A is gonna be 90 degrees and PA is gonna be pressure at that point. So you remember the angles start from here. So 90 degree from here is the theta A, somewhere like here. Theta A is like here. Maximum pressure, theta is gonna be here. Alright, so coefficient of friction 0.25. PA I don't have it. B I have it, 1.25. Radius, we got it, 6. Theta A is 90 degrees. So this denominator will be 1. this integral, the radius is 6, a is that distance is 10. Alright, so remember when you take the integral, these guys must be in radian. So if I put this into a calculator, mf is gonna come out something times PA. Right, so that something is this fraction times this integral. So I have the answer here, let me see. MF for that problem is going to be 3.728 times the PA. So let me remember that. 3.728 PA. 3.728 PA. Units, you gotta make sure that you know if everything is in inches, then pressure could be in PSI, right? So and then pressure PSI, then the moment is gonna be pound inch. Alright, so this is what I got for MF. 3.728, okay, pound inch. Okay, so we need to figure out also the moment caused by the normal force. So let me write that formula too. Let's see if I can remember this. PABRA. So MN PABRA divided by sine of theta A. Integration again from 8.13 to 98.13. What the integral was, by the way, sine of theta squared d theta. There you go. So again, we have the B, we have the R, we have the A. Theta A is again 90 degrees. This integral is going to come out in terms of PA2. Gonna be equal to, you can put it into your calculator. Let me see the result here. 69.41 69.41 PA. Alright, so we found these two, and then the question now is whether this system is self-energizing or not. Alright, so for this one it's a bit tricky. It's not easy. The reason is, if you look at here, sometimes the moment caused by the friction is actually helping. So if you look at here, friction force here, you see here, for these friction forces is actually pushing the arm upward, so disengaging the system. Right, it's pushing it up, but as soon as I pass this point, this top point, the story changes. Here is like passing the pivot, but after that it's gonna go like this. So it's like, you see, now this moment caused by this friction force is actually pushing this down and engaging it more. But so now the question is, which one is larger? Engagement is larger or disengagement? And for that, notice something. The pressure here is the smallest, and then as we go to the other side, pressure gets bigger and bigger. So it looks like friction force here, is bigger. And those differential elements on the right side are bigger. Here they are smaller. So you remember the right side was actually helping to engage more, but the left side was disengaging. So the right side, the friction force is larger, and then by the way also the arm is larger. If you look at here, see this arm, this is the arm here, but for friction forces here the arm is like this, so this is smaller. So if you guys like, you can take the integral, set up an integral and find that integral and see whether you have at the end positive or negative. But It seems like to me that the system, even without calculation, this system is self-energizing. So then this equation is valid. So let me write it. So let's go back to the lecture notes. We said that for non-self-locking, this is a relationship between actuating force and those guys. And for self-energizing, this is a relationship. This is this, right? Alright, so let me write that now. Alright, so F equals Mn minus Mf divided by C. Yeah, alright. So what Mn was? 69.4 minus the other one is 3.728 times PA. The other one was times PA2. So I have this PA for here. Divided by C, I already figured the C was how much C was 20 inches. Then actuating force, we know it was 90 pounds. So from here, you guys are gonna find PA. Max pressure, as I said earlier, is gonna happen somewhere like here. So max pressure is equal to, let me see, I have the number here. So max pressure is gonna come out 27.4. 27.4 psi is the max pressure. Is this what the problem was asking? Let me see this. Yeah, it says find the maximum pressure on the shoe. Okay, so you remember I said that that's gonna happen right here. So we found that, and then the next question says, next part says that, okay, now that you got that, find the torque applied to the disc or cylinder. So that torque, braking torque, we have to evaluate this integral F R dN from theta 1 to theta 2. So we had a formula for the 16.6 for that. So that's going to be valid here too, that equation. Let me go up. I have a 16.6 here. Where is it? Okay, this guy. So F, now that I have the PA, I can evaluate this in this torque. So let's write it. F PA. Oh no, not this. FPA B the R squared divided by sine of theta A. And then what? Cosine of theta 1 minus cosine of theta 2. Again, we got everything. We have everything, right? So friction coefficient was how much? I forgot that guy. Was it 0.2 what? 0.25. PA 27.4. The B, what B was 1.25. What was the radius? Is 6. Divided by theta A is 90 degrees. Alright, then cosine of theta 1 was 8.13 minus cosine of 98.13. There you go. This is gonna give me that pound inch. So let me look at here. I have the solution here. Yeah. You put all these guys here. It's gonna give us 348.7. 348.7. 348.7 pound inch. There you go. This is the torque, right? Braking torque on the cylinder. Alright, so you saw that which set of equations I need to use for a problem like this. You just look at the function of this, you know, how this actuates, how's the mechanics of this, and then decide about which equation, which set of equations you guys can use. I have them in note, and I have them also here in the PowerPoint and also your book. So you can use either one. Let's see if I can open this quickly. Yeah. Why? What's going on? Let's open it. Yeah, so we go down. Yeah, you see, equation 16.6 is here, and for this type, the equations MF that I use, MN that I used, 16.2, 16.3 is here, right, and the rest. So we can use these guys. Alright, I hope this was useful.